Hey everyone, I'm David Room. Tonight we're going to be doing some more 3D mesh processing with Python. I've been thinking about some new capabilities that I've been wanting to build for quite a while, and I kind of had some good thoughts the other day about how to do it. And I thought it would be kind of a nice thing to share because it's a little bit maybe more general of a thing than a lot of the stuff that I build. So oftentimes when I do these videos, I'm working on very specific aspects of my project. And this time I'm going to be trying to build some more general 3D capability, specifically a process for using a manifold 3D mesh that has some certain nice properties to cut or do something like a boolean difference against a non-manifold 3D mesh. And this is something that will be useful for my project, which is programmatic creation of these spaceship 3D models, both low poly and high detail, high poly models. And it's something that doesn't really seem to exist in a lot of tool sets, at least that I found. And honestly, whether or not it does exist, it's fun to try to implement these things yourself, kind of like a geometry puzzle, something that's fun to think about and try and visualize. Also, while I'm at it today, I use this library called trimesh. So when I'm doing this 3D mesh processing with Python, I have a simple mesh data format that's numpy arrays, so a numpy array of vertices and a numpy array of base indices for a triangle mesh. And then for certain capabilities that I didn't want to implement myself, I use some other libraries such as Shapely for 2D stuff and a library called trimesh for 3D mesh processing. And trimesh is a nice library, but there's a lot of aspects to it that I don't really like. It's very object oriented. So in a lot of my code, I sort of build this thin wrapper around trimesh that is more to my liking as far as the way I want to write code. So what we're going to be doing today, kind of along with this mesh cutting operation, is I wanted to take a look at a new version of trimesh because they've switched to a different engine for doing mesh booleans. And recently, when I've kind of gone back away from game development recently towards this high detail 3D ship modeling with greebles and stuff. I'm starting to use the mesh booleans again. And supposedly this new backend for mesh booleans is way faster. And I want to see if that's the case. And in the past, when I've tried to upgrade trimesh, I run into issues where certain behaviors don't work right. It kind of breaks my code. And the thing is today, in the process of doing this mesh cutting thing that I want to build, we're probably going to build some nice test cases that are easy to visualize, and we're going to also hit some different trimesh behavior and trimesh wrappers in my code beyond just the mesh booleans thing. So it would be a good time to test a new version of trimesh and see if there's behavior that's changed, if things have broken, stuff like that. So without further ado, let's get into it. I've got some water here, and I've got a Point black cherry cream soda. So I'm not drinking beer. Has been a long day, but I'm not drinking beer. I'm drinking nice cherry cream soda. So let's get into it. And I'm going to put on a little bit of music here. I was wanting to stream again this weekend because recently I've had a lot of new viewers on my channel. YouTube seems to be doing a better job of, or not a better job, but YouTube is starting to try to promote my stuff a little bit more. And Uh, I wanted to stream, but I kind of worked on something else instead, which was experimenting with lighting, and also my wife got a stream deck, so she does some streaming on her channel, usually on Mondays, and she got a stream deck, and we experimented with that, kind of setting it up so I can actually switch scenes here with the stream deck. So that's nice. I can see I'm going to run into some problems with things here, but yeah, we'll be sticking in this scene, so I don't need to have that set up. And anyway, I figured out a really nice lighting setup, but I just didn't have time to do that tonight. So watch for that on a new stream. But some new capabilities coming, and I want to take everything up a notch a little bit with what I'm doing, if people are going to watch. So I think what I want to do first. Actually, let me get some music started. So I think what I'm going to do first is build out a test case for the cutting operation that I want to do, and I'm going to build it in such a way that we can test normal mesh booleans and this new intersect a manifold with a non-manifold mesh capability that we're going to build. So we'll do that first, and then we can kind of get into maybe either looking at a new version of trimesh and then looking at this new capability. So I don't look at my unit tests super often, so let's see what we have in here. Okay, so I have a lot of my wrappers around slicing in this module called Slice, which is not a very good name because it is actually a reserved word in Python. But let's just see what this test is doing right now. Tools, and I'm using, let's see, where am I? Tools. Oh, test slice isn't in tools, that's why. It's in XP. Oh. So we've got a box for slicing it like that. Yeah. Okay. So this slice module is basically functionality for if you have a mesh, cutting it with a plane. And there's some functionality in here that wraps the process of like cutting a mesh with multiple planes, because that's something that you often want to do in my process. Like you want to cut like a chunk out of it. I think what I actually want to do is, and for some reason this is something that's kind of odd, is that the trimesh wrapper around this slicing operation returns a mesh where there are like duplicate vertices for each triangle, and this is like a constant source of grief for me in my project. So I'm curious to see if the new version of trimesh has fixed this, because it doesn't seem like it doesn't seem like normal behavior, I guess. So actually, let's just first do a test for like a single slice. Some of this unit test writing is overdue. So this cylinder with 4 subdivisions is basically just like a prism. And actually, you know what? I think there might be instead of doing a cylinder, I'm just going to do a box. And then we can kind of double check and really make sure that what we expect to be going on is what's going on here. This isn't exactly what's going on below, but something like it. So we'll rotate it 45 degrees around the y-axis, and we'll just take a look at it here, see if this is what we expect. Get the right test in here, so test slice.py, test. Yep, okay. Now, something I'm gonna add back in here. My polyscope viewer. Is print. I always like to have this printout so like whenever I'm viewing a mesh, I can see how many... Hey Doug, how are you doing this evening? I like to print out some info so I can see something about it. Let's see, and I'm just going to make sure that that's the number of vertices and faces that I expect. So vertices 8, faces 12. Yeah, that's exactly right, because there's 8 vertices, 4 on each end, and then 12 faces because there's 6. There's 6 faces, but each face has 2 triangles. Okay, so that is expected. Now, let's just verify this current slicing behavior where the triangles are separated. Doug says he's doing pretty well, nothing too exciting. Yeah, I think it's sometimes nice to have a not too exciting not too exciting time. So let's see here. So we're going to slice it with a normal and position. So our normal, we'll just use the up, and the plane position will be and let's see here. Yeah, okay, so our new mesh has 16 vertices and 9 faces. And see, this is that duplication that I'm talking about. And not only are things duplicated, you have potentially redundant faces, right? And that's why this requires some care, because this face can just be turned into 2. This face can be just turned into 1. But see, we also have 16 faces, and that's because we've got 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15, 16, something, right? It's kind of like not what you'd expect. The connectivity of it is sort of busted. So that is unfortunate behavior, but it's what we're expecting. I'm just going to go ahead and add an assertion in right here, so we can tell if we get a new version of trimesh, something broke. So, and you know, in my code, meshes are just tuples. So the first element of the tuple is the vertices, and the second element is the faces. So you'll sometimes see this 0, 1. It's not the cleanest thing, but it's like maximally simple, and that's kind of what I'm going for here. So the shape of the vertices of the slice is going to be 16, 3. I swear I can type. Jeez. Okay, and then the faces is going to be 9, 3. And then let's add an assertion in just for the original mesh too. So that is going to be, what was it, 8 and 12. Just put this in the debug. Okay, now we can turn debug off and run this again, and it test should pass. Okay. So now let's do something a little fancier. A little bit fancier. So we're gonna test some operations, and I'm actually not gonna do this here. I'm gonna do this in tools. So I kind of have this staggered thing where as I build new functionality, it goes in tools first, and then it goes into modeling, experimental, and then into modeling. So we're going to do this in tools, and I think we're going to test what should we call this? Test we'll call it slice plus. It's kind of a slice, maybe bool plus, because it's like a, it can be like a better mesh booleans. And then when we're making unit tests, we just make functions that have a test prefix. I like bool plus, that's kind of nice. And just for starters, we can grab these imports. And what should we do? Let's take make a nice, not super simple, not super complicated test case. So we're going to do a cube. And we'll actually give it a couple of 45-degree rotations. And then what we're gonna like intersect a cylinder with the top of it. So okay, so let's just take a look at this. Let's go back here. Test tools. Okay. Actually, we're gonna do even one more. So we're gonna do and it doesn't matter if this is actually aligned, it's the way I expect. In fact, it's okay if it's not, because we want something with kind of a irregular shape that we can intersect other shapes with. And then here's what we're gonna do. So we're gonna actually slice it off at the top and use the slice. Use the slice for the piece that we're gonna work on. So slice equals mesh dot slice dot slice mesh. Mesh z hat, and again we'll go like 0.5, and then this time we're going to retriangulate and process. So we've got to do this two-step where we retriangulate, actually 3 steps. Retriangulate, concatenate, and process. If I look throughout the code, you see this. And actually, it looks like I usually process first. That actually might be the source of some of my problems, is like doing these 3 steps in the wrong order. I think we want to retriangulate, concat, and then process. That was my first thought, so we're going to do that. So retriangulate, concatenate, and process. And then this mesh should look good at this point. So we shouldn't have any unexpected counts of faces or anything when we look at the wireframe. And I'll add an assertion in. once we confirm that here. So we've got this kind of pyramid, and would expect this. Oh, not quite. So you saw there's that extra face. So this I'm going to have to just tweak the trimesh tolerance on before we do this. So it's usually the merge tolerance that you have to mess with. Tall.merge, and then we have to like this. We're just gonna set it back. So we're done. This should look nicer. Nope, it's still there. That's a bummer. Let me just see if this fixes it. No, that's crazy. That's interesting. What's going on here? Well, I don't like that one bit. Oh. I think I know what's going on. This is why I've got to write a wrapper that does this. No, that still isn't it. What's going on? Now I'm really confused, you guys. This is interesting. I'm glad I did this because this might have really tripped me up later, because I wouldn't have expected the simple case to not work. Okay, so in the original mesh, we've got 6 faces like we would expect. Okay. So oh, I'm dumb. So I was doing all this work on the original mesh, not on the slice. That would explain it. I might not need any of this crap. All right. Well, we've got some visualization stuff if we do run into trouble. So let's yeah. All right. Jeez. Yeah. So we still have that, but now if we turn on this merge, it's usually a problem with the merge. Okay, now I'm really confused, you guys. So do I have a different threshold in here for apps? That's what that is. Yeah. It's a different threshold. And that is only used there, right? Okay, we're gonna fix this. We're gonna fix this problem. I think collinear is the term I'm looking for, right? Yeah. So, oh my gosh. So this is a check that I'm doing to see if points that line the same line are collinear, because you can end up with these extra points, and if you have extra points, we want to get rid of them. They weren't being gotten rid of here. So This is in Triangulate. There's probably there's probably a better way to do this, but let's see if this fixes it. Oops, equals. For crying out loud. Oh. What? Oh. Oh, there is another problem. There we go. Okay, so I think, yeah, the problem is that I did need this guy. And let me see if I get rid of these. This might actually still work now. Yeah, okay. So the problem was that this step is necessary first. Because it doesn't matter, the collinear checking is not doing anything because those vertices are distinct. So we need to make sure all of the close enough vertices are merged first, then retriangulate and rebuild the facets, and then concatenate. And then actually, yeah, and this thing returns a list of meshes. That's why we need to do the process no validate again after concatenating. Ah, jeez. Okay, I'm really glad I went through this because I saved myself a ton of future grief, and this is all ready to go if we run into issues with it. So, okay, so now what I want to do is I want to relegate this stuff to debug view, and then now we're going to do some assertions. So assert that the slice, so it's the pyramid, it's a 3-sided pyramid, so it's going to have 1, 2, 3, 4 vertices. So it's going to be 4 by 3 for the vertices, and it has 1, 2, 3, 4 faces. So the faces shape is also going to be 4 by 3, and let's see if that passes. Nope. And it's just because those zeros were extra. Okay. 3 by 3. Oh yeah, because there's only 3 faces. There isn't a face on the bottom. Okay. All right, that is working. So now we have a couple of tests that we're gonna do. So import. So we're going to build a cylinder now that we're going to be intersecting this shape with. So our cylinder is going to be a cylinder. We'll do it of length 1, of radius 0.25. We'll do a nice high number of subdivisions, like 12, so we get some resolution out of it. And we're going to rotate it so so it is upright, and then I'm going to look at our slice and the cylinder. Okay, and that's too big. Okay, but gonna bring this slice down too, so yeah, okay. So something like this, and then let's just also translate our sliced mesh a little bit so we're intersecting multiple faces. So we actually want to go, yeah, we want to go in negative x and negative y. too far. Now I'm confused. Okay, so there's at 0. So we want to bring, yeah, we want to bring this in positive y and negative x by just a little bit. Yeah, there we go. So now we're intersecting all 3 of our faces of the slice with that cylinder. And we can actually make the cylinder a little bit bigger too. Yeah. Okay. So what we want to be able to do is we want to use this, we want to be able to use this cylinder to cut out of this piece. But typically when we do unions, both, like all the meshes involved need to be manifold. So what I'm going to do is I'm going to first make the slice manifold, a manifold version of the slice, using some special tools that we have. So we have tools for making spacecraft panels, and I think this should do what we want. BK Rex 444 says hello. Hello, how are you doing tonight? Okay. Slice. And we're gonna solidify this direction. And let's take a look at both of them again. Yeah, and the solidify panel isn't going to do what I want. Why did that not work? That's interesting. Let's just take a look at it by itself. Okay, no, it is solid. The problem, no, it is solid. It's just it kind of doesn't look like it is from the bottom. Let's see, what is this expecting? I'm confused now. I thought this would work. But see, we've got these perfectly thin edges here. What gives with that? Actually, there might be a better function here in panel. Let's try this. Ah, that's odd. I'm getting a strange error here when I'm trying to do this solidification operation. Gotta look more closely at this error message. Okay. Plus. Oh, dumb. This is returning something else that we can toss out. Yeah, okay. And I think the problem is that this thing is just too steep. We've got to kind of flatten it out a little bit too. So I'm going to do that here. Yep, and now let's get rid of some of this unnecessary stuff. So what we've done here is we've made a mesh that should be manifold and watertight that we can cut. And let's just assert that. So TM is watertight. Yep, okay, so it is watertight. Okay. So now that we've got our two meshes, we can try to cut them. So difference. So we're going to be cutting SL manifold with our cylinder, and we'll assert that the results, this mu.tm is converting it to trimesh objects, which has that watertight check. I could actually probably write my own watertight check, as long as that's not also checking for self-intersections. I think that should be pretty easy to check, because it would basically mean that the mesh doesn't have any open boundaries. And if you wanted to add a intersection check too, if it didn't have any open boundaries and you didn't have faces intersecting with each other, then it would be watertight. So let's take a look at this. SL diff dot is watertight, and then let's take a look at it. Okay, so here we go. Cut, there it is, and it is watertight. You can see the interior thickness. Okay, so what we want to do now is we basically want to be able to do the same thing, but just with the original non-manifold version of this, right? So like something that we could do now, if we wanted that functionality, we could do this mesh difference operation, and then we could, like, say, peel off this top part. But I don't really want to do that. And actually, you know, we don't even have to use this panel. What am I even doing here? Yeah, there's a simpler way to do this, but that's fine. That's fine for now. Okay, so what do we want to do? So this is our original full, like, so we're gonna call this so SL diff is going to be mu.difference, or not mu but difference, but bool plus dot difference of SL cylinder, and then this will certainly not be watertight, and stick with this. Okay, so now we've got our test case. Let's and we could add some other assertions too. I'm gonna close plus. Okay. So now we're gonna actually make it. Okay, so the question is now, how are we gonna do this? So we're gonna do a bunch of transformations, and then we're gonna be doing some 2D boolean operations on individual facets. Okay, so and you know, there's gonna have to be, there's going to be cases of manifold meshes that aren't going to play nice with this, but I think for the most part they are, and I'm not going to worry about those edge cases right now. So we're going to call this plus, and get rid of this because we're using U now. Okay. So okay, so in bool plus now, we want our mesh, which is not manifold, and our cutter, which is. And we're going to return a mesh. I'm going to just copy these things for now. I've talked about this before, but all of the types in mesh are just simple aliases for things. So a mesh is just a tuple of verts and faces, and verts and faces are just aliases for ND arrays. It's like very simple. Okay, so okay. So the first thing that we're going to do is we're going to separate out our mesh into its constituent facets. So not triangles, but polygonal facets. And I think we can do, I don't really want, let's see, do I want facet boundaries? Let's see. Facets, normals, all. Okay. I think this is also something that I need to fix, is trimesh doesn't return single triangle facets in this, and that causes problems. Facets normals all, that's what it's called. Okay, so for facet normal in, okay, so we're gonna set up a transformation of the cutter and each facet into a coordinate system where the normal of the facet is going up in the z direction. So what we need to do here is find a rotation by what is the name of that function? Rotation normal. And that just finds the rotation that takes a particular normal to z. So now and actually I think, let's see, facet boundaries. See, this is stuff that I need to rewrite too, but I think we can kind of do this in the not the most efficient way, and it'll still work. So, not too worried about that. So, we're going to extract a mesh now that corresponds to that facet. So select subset mesh, faces, facet, facet, and we can transform both of these now by rotation, by rot. So facet mesh equals mu dot rotate mesh. And we can call cutter okay, now if we view these, we should see something basically expected here. So okay, and I'm just gonna get rid of some of these other things. Actually, we'll just keep this one. Let's see here. We'll keep this one. Okay, yeah, that was looking right, and this one, get rid of, okay. Okay, so here's our shape. Now we have each of the facets is aligned in Z. And the vertical position in Z doesn't matter. But what matters is that it's aligned so that the normal of that facet is in Z. And you know what? Just to make things a little bit muddier here. No, I'm not going to worry about that now. I don't think we need to do that. Okay. So, okay, so what we're going to do now is do a cutting operation in 2D on the individual facet using Shapely. And there's going to be some different gotchas there. So the first thing that we're going to want to do is we've got to find the Z position of the facet and then slice the original mesh by that and find the boundary, and then also find the boundary of the facet. So we'll find the so find the longest boundary of the facet mesh and find this. I think there should be a find longest boundary verts somewhere. That's in greeble util. Facet boundary axis. Facet boundary. Okay. So that's that, and this is still 3D here. Right. So that's still 3D, and then we need to find the Z position. So let's see. So we can say facet Z equals NP. Oh, I gotta import numpy. Got enough wrappers around numpy stuff even though I don't need to import it a lot of times. So we're gonna take this, the Z dimension, the mean, and then we're gonna slice the cutter, the rotated cutter at Z equals FC. So this is where slice comes in. Slice dot slice mesh rot. The plane normal is Z hat, and the plane position is that Z height. Now, we don't care right here whether we're taking the part that's above or below, because we just need that boundary. But that boundary is going to need to be nice. So so I've got to clean this up with that same sequence of operations that we were doing here. And you know, you could maybe get away without. Actually, let's just think about this for a second before I do this. What do we need? We only care about the points that are on that plane. Is there a way that I can eliminate the stuff that I don't care about and still keep the connectivity information? Because I want the connectivity. I guess I'm not using the connectivity. No, I am using the connectivity. Yeah, I mean, I guess you could weed this down. You could weed this down to the But I think we still have to do the merge. Yeah, okay, so here's what we're gonna do. We're gonna skip the retriangulate because I don't think it's gonna hurt anything in Shapely if we have those extra vertices. But I'm gonna add it to do for later. So, oh, actually, you know what? We can actually just do that. We can do the, that's what I was thinking of. We can do the getting rid of collinear points in 2D at the end. So we just need to process this. So we need to process no validate, and then there would be different ways to do this. Obviously, but I'm gonna there's probably a better way to do this. But I'm just gonna cheat and just use the boundary finding to find the longest boundary. So cut boundary indexes is and then the cut boundary is going to be cut cell 0. Yeah. Okay. So now we should have two 3D loops that are coplanar. The z's constant can be tossed, that we can do a Shapely operation on. So let's see what this does, and let's take a look at our loops. Plot loops 3D of FB and CB. So FB being the fast boundary and CB being the cutter boundary. Yep, look at that. Okay. This is good. This is what we want. Now we can do the cutting operation. And if we are going to do the, we could remove collinear points here. But we're not going to bother with that right now. So I have a Shapely wrapper now, and I want to see if that has a nice way to do what I'm trying to do here. So difference. I think I want this guy. Section. Do I have another? Yeah, okay, we'll use this guy for now. numpy diff. Difference classic of studs. Loops to polys. And this is just some convenience functions for converting converting arrays of numpy loops or numpy vertices to shapely shapes. And just yeah. And we don't have to toss out the z dimension here because because Shapely is going to do that for us, and we already have the z operating point here, so that's going to be that. Now we can plot oh, we got to convert this back. Oh, okay. So this is not, this is not going to be quite what we want eventually, because this is going to lose whole information. So poly with, oh, there we go. Poly with holes diverts. Look at that. So for now, we're just going to ignore, holes, but we'll test that in a bit. And yeah, let's just, we'll ignore holes for now. I think probably we've been going long enough tonight that I don't want to get into the holes case, but like that's going to be something that we're going to have to handle here as well. Because like if you land that cylinder in the middle of a face, it's going to be a hole, right? It's going to cut a hole out of the middle. And we'll have to deal with that. But that's actually, I think that's more just kind of a mechanical thing than famous last words, but I think that's more of a mechanical thing than anything else. Okay, so let's see if we got our types of things right. Yep. Okay, so now what we have to do is we're going to make a results array here. Okay, so now we have to triangulate this guy. Mesh is triangulate. And see, there's the holes. So actually, I think maybe it isn't hard at all. It's just going to be triangulate poly holes with fbdiff and fbdiff holes, and let's actually, we can just handle this right here. So holes, and this actually returns, oh, it does. Does it? Yeah, it's making sure this is 2D, and it's returning points and faces. Oh, triangulate poly holes 3D. There we go. No, we don't need this 3D version. 3D boundary and interior. It's a conversion to 2D. Oh, yeah. And we don't need to keep an original 3D version to map back, because we know that this is all just going to be constant. So all we have to do now here is we have to take this guy and add in the Z back. Oh, actually no, and this is already, fbdiff is already, it's already 3D, right? Yeah. Yeah, okay, it's already 3D. So we just need to add, wait, do we even need to add FC to it? Because I never subtracted. No, yeah, I think we're good. I think we're good, because this is all still 3D. This is 3D, this is 3D. I thought I had stuff in. I thought I had stuff in here that stripped the third dimension off, but no, I don't. Okay, so I guess we're good. I guess this is all 3D. Maybe this could be also something just to note to like do all of the shapely stuff in 2D for clarity. Should see. But we don't need to do that right now. Okay, so we don't need that. I think we're actually good to go, and we can just toss this in res, and then at the end here we just want to, and we don't have to retriangulate because we just triangulated, so that should be good. We just have to concat and process. So concatenating is just going to turn that list of meshes into a single mesh. Processing is going to unify vertices that are really similar. So, and process no validate. So I'm using trimesh for process, but no validate disables validate, which does some goofy stuff, like it can flip faces around, and just, I think it's kind of designed for manifold meshes, which this is definitely not going to be. So okay, so now we're returning a result. Let's see. Okay, and this failed. Oh, okay. Yep. Good. So it did catch it. did catch it there when we went to triangulate it. So we do need to strip off the... This is kind of like a weird... diff verts diff bases. So we want to strip off the z here. X of... Oh, actually, I don't want to strip it here. I want to strip it before we go into this. Here. Here's where I want to strip it. Because then all of this stuff will be in 2D. And then we can reattach here. So FB diff verts smu.attach z fz, and then FB diff mesh is just these two. Okay. Okay. Now I'm plotting loops 3D that are 2D. So this will be plot loops 2D. Almost done here. Okay. Ah, yep, and I forgot an important step. I forgot a very important step here, which is that these guys need to be rotated back. So this now, this is fun. So mesh, we're gonna rotate mesh, and actually, you know, we can actually just rotate the verts. Dot rotate verts. And we're going to use the inverse of that rotation matrix that we found, which is, because rotation matrices are special, it's just the transpose. So yeah, okay. There we go. Okay. Now let's test the case where we have holes. And if that works, then we're gonna call it good. We're gonna quit while we're ahead here. Okay, so what I'm going to do is I'm actually, instead of moving SL, I'm going to move the cylinder, because that's what we're cutting with. So So that was our original case without so we basically just need to have a smaller cylinder and shift it in a more extreme way. So we'll do something like this, and I'm gonna have to look at this to see where it needs to go, but we'll just try that for starters. Not quite. It's like it needs to go from this point, it needs to go in the positive y direction. Okay. Yeah, like that. All right. Now let's see if it works with holes. Yep. So here, there's no overlap at all, so the face isn't altered. Now here it's going to be a hole, and it fails. Okay. So what's the problem here? Linear ring object has no attribute exterior. X and poly dot interiors. Interiors. Linear ring. Okay. Linear ring. Oh, you know what? I bet this is a typo. Actually, let's just take a look at the Shapely API here. Okay, I think I don't even need chords. I think I can just convert this. Linear ring. Let me just try this. Can I just... Nope. Array is zero-dimensional. Just doing a quick Googling here. So linear ring, one or more line segments closed. Ring.chords. Okay, so it does have chords. Okay, dot chords. Yep, there we go. There it was. So for whatever reason, this wasn't correct. I'm curious, poly with holes. Okay, look at that. I'm only actually using it here, so I must have just written that up without actually properly testing it. But there it is. Now, let's do one more test, and just because the angle of this these faces is so shallow, it's kind of hard to tell that we're transforming the cylinder right. I'm sure that we are, but just to make it a little trickier, I'm gonna add an additional rotation on this just to make sure that it looks correct. So we're gonna rotate this with a let's see here. Yeah, I suppose we could do a rotation in Y, like pretty extreme, something like this. And then just, I need to, with polyscope, I've got this viewer going, but it needs to be a little bit better. But even without that, let's just throw that on here, and we should be able to see the vertices. Okay, so here we've got this, and it looks like we should still have a hole, right? Yep, and you're seeing that skewed cylinder shape. Yeah, okay, well that seems to be working. I'm pretty satisfied. And one final check. We'll take this into Blender and just kind of verify that we don't have any extra nonsense going on. So what I'm going to do is I'm going to just turn the subdivisions of this down just so we don't have quite so many pieces. Then we're going to open our Blender viewer. Ports spp ev dot view mesh, and then we're gonna concat a we're gonna cat these two together and take a look. Okay. So here's our shape. Actually, to tweak my camera clip start, so we've got some extra room here. Okay, so this is a single mesh, but when we go into edit mode with tab, we can separate by loose parts, and we should just have two. Good. So we have just two loose parts. And then do we see what we expect to see here for vertex and face counts? So this guy, vertices 10. Yeah, 10 because there's an extra in the middle there. And then here we should have 1, 2, 3, 4, 5, 6, 7, 8. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Oh, okay, so this is interesting. Okay, this is interesting. So we do have extra geometry here. I was thinking we didn't have to re-triangulate. But the way this cutter ends up happening, yeah, and see, this is the consequence of that step that I was talking about, where we could eliminate collinear faces. Okay, this is good. This is a nice test, and actually, we're almost certainly going to be able to see this in in here, so we're not going to need to look at it in Blender again to be able to see that. Yep. Okay. So let's actually deal with that. And I think we can actually deal with that right here while we're in 2D mode. We can remove collinear extra points from here with a function that I'm using in retriangulate. Remove extroverts, triangulate dot, yeah, it's actually just in triangulate, remove triangulate dot remove extroverts. CB is triangulate dot remove extroverts. And we might have to tweak that tolerance, but I don't think we will because we didn't before. Whoops. Triangulate. Whoops. CB1 dot shape. Oh, this is indices that we can keep. So CB. Yeah. You can see there the loop. The loop is just 4 vertices. That looks better. And let's just take a look at it once more in Blender, and then we're going to call it good for tonight. So we made some great progress on this functionality. And actually what I'll just do quick too is I'll show you what the purpose of this is going to be. So, whoops, okay, edit mode, separate by loose parts. There we go. And then now we've got 8 vertices here. 8 vertices, 18 faces. Let's see if we can count the faces and see if that looks good. Camera clip start. 5 centimeters. Okay, so 18 faces. We've got 1, 2, 3, 4, 5, 6, 7, 8. Faces 9, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. This is all looking really good. So the purpose of this, and I also was talking about looking at new trimesh functionality. We'll save that for another time. But the purpose of all this is in my spacecraft greebling, so I have this capability where I am building these ships, and I have different devices and greebles and structures on them, and then I want to make panels. And what I was doing a while back is cutting these panels with booleans. So like after I had solidified them into booleans like this, then I was cutting them with these devices. The problem with that is you have to scale up the devices to get a nice little boundary around where you're going to cut. I'm just going to pause the music here while we finish up. So you have to scale up the devices, and that doesn't always do what you want. What you really want to do is some kind of like outdent or inset, like a negative inset on the boundary. And I think the best way to do that is, so like when I make these panels, what I'm doing is I am, slicing out these things kind of like we were doing at the beginning, and kind of solidifying them. So what would be ideal is if I could actually do that cutting or boundary finding on the non-manifold mesh. And so that's what this is going to be for. So we can do things, and we want to be able to handle things like devices going across edges of panels, right? We don't always want to be stuck. We don't always want to be stuck doing these cuts. Just on a single plane, like here, for instance. Just delete this guy, delete this guy, delete this guy. So like this shield ring is like cutting through these three different faces here, right? And the thing is like I have some really cool tools for operating on sort of non-manifold meshes. So like once that cut was done, we could indent it, outdent it. You could make an indented and outdented version to add bevels and stuff. And I think that could work pretty well, and it might work more reliably than booleans. Because whenever you start to solidify these kind of complex shapes, you run into little edge cases where things don't work quite right, and it's not a big deal just for looking at things visually. I'm not demanding this stuff to be perfect, but it breaks down when you're trying to do these booleans on it. So the goal here is to have like more tools in the toolbox as far as kind of intersecting these different shapes together and adding details and things. And I think this is going to do a lot for us in that regard. So that's it for tonight. We built a nice piece of functionality that I think is going to really help the greebling stuff that I'm working on a lot. And thanks everybody for stopping by, hanging out. Thanks, Doug, especially. It's always good to see you in the chat. And stay tuned. I'll be probably streaming again some other time this week because I'm trying to build some momentum on this, and maybe I'll have my cool lighting setup then. So thanks again for coming, everybody, and have a good night.